Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is going to be a bit of a strange talk for me because I'm principally a security guy, but I find that in order to actually innovate in computer security, sometimes you have to get into the hardware, and we discovered some interesting things along the way, and we'll talk about computing on this intermittent power and how horrible it is for people who have to write software. So lots of fun pain. But first I'd like to say thank you for welcoming me here. I just stopped by Parker's Piece, I believe that's the area of which it's called, and I have to thank, maybe it was George or whoever does any security research on welcoming me, because I took this photo, and then I later zoomed in, I looked in at the trees, and I noticed that you guys actually welcomed me. So I have to thank you for the decorations in the sky there. I don't know how you did that. Okay. So again, I'm largely a security guy. Some folks know about my research on the security of medical devices and looking at reverse engineering, for instance, contactless credit cards. But today I want to talk about the journey we took and the interesting research we found when trying to use this lovely device. So in 2006, Josh Smith, previously at Intel, came up with this, what I thought was quite an innovative device. It behaved like a UHF RFID tag, but it was completely programmable. It had a microcontroller, it had no battery, and you could write C code and compile your programs to get it to run on this device. And we thought, wow, that's really interesting. We can finally start to experiment with interesting security protocols. So I had my student do some simple crypto, and she compiled it and put it onto the tag, and it wouldn't run. Because this machine would reboot about every 100 milliseconds because of loss of power. It would be harvesting energy from a 915 megahertz UHF RFID reader, and then it would just die. So we got halfway through, I think, reduced round RC5, which in plain terms is a very simple, very fast cipher that should work on any platform, but it didn't work on this one. So this talk is largely about how to get computation to work well despite extremely fickle power sources, to make the programmer get work done without having to think so carefully about what's going on in energy. But I think this is a really interesting area for research because these devices are shrinking. And I'll just go through a couple examples of the ever-shrinking computer. This is a recent press release from Stanford about a device that's designed to swim through the bloodstream. The idea being putting medical devices literally into your bloodstream. And what's interesting is they've designed it to be wirelessly powered because, of course, putting a battery through your bloodstream, probably not a good idea. Might not fit either. In the medical device world, there's quite a bit of innovation. Today, pacemakers are typically about yay big, and they're implanted beneath the clavicle. But one of the largest medical device manufacturers has created an actual prototype that's extremely small. I'm sorry, I don't have any British coins on me at the moment. But it's extremely small. Maybe you have Tic Tacs here? I don't know. But it's extremely small, and it can actually be implanted in the body using a catheter rather than doing any kind of invasive surgery. There's some other interesting work going on, actually in collaboration with Microsoft Research in Seattle and UW on this augmented reality contact lens. Is anyone here working on that project by any chance? I find this fascinating that you're able to put computers inside contact lenses such that you can have augmented reality. So as you're walking around, you can see annotations. And it's already been done with trials on rabbits. And at the hardware level, there's some really interesting research going on. With, for instance, subthreshold circuits to get computers running at extremely low power. Is this your research by any chance? Anyhow. And extremely small and being applied to medical devices. But there's a big problem. And the big problem in my mind is the energy bottleneck, typically the battery. So with that pacemaker that was the size of a Tic Tac, they don't have a way to power the chip. They figured everything out except how to get power to it. So the power problem is holding up the innovation of the medical device. With the contact lens, they've tried all sorts of ways to power it, but they haven't found any that really fit their specifications, the constraints of their system. The space constraints are extremely constraining. And as you can imagine, you really don't want to put a battery in your eye. It's not an ideal location to have something that heats up. And then with that device that's swimming through the bloodstream, they point out that energy simply doesn't have a Moore's law. Batteries don't have a Moore's law. It does not shrink at that kind of rate. So it's going to be difficult to shrink these batteries down. To give you a more concrete example, who's used a sensor mote? Oh, many of you. Okay. So this is the typical device most people think of, at least I think of when I hear the name sensor mote. What's interesting is it has what I call a backpack of batteries, 2 AA batteries that take up about 66% of the entire weight of the device. And I find this amazing that we tolerate that kind of volume and that kind of weight. There are other innovative ways to make these devices last long. You just add lots of batteries. I think that's maybe a little bit silly. I certainly wouldn't want to implant that in me. But if you are willing to implant a device in you, say a pacemaker, you might be interested to know that every 5 years you'll need a surgical replacement of your device because the battery begins to run low. There's single-use batteries. And moreover, if you're willing to take a Dremel to a pacemaker that you found in a medical waste container, you'll find that the battery takes up over half of the volume of the device and well over half of the weight. And even worse, a very small sliver of that energy is actually used for pacing of the cardiac tissue. Most of the energy is used on what I would consider overhead of the system. So these systems are not exactly the most energy efficient in my mind. Now, there are many ways to take a look at this, but I view this as a problem of abstractions that don't quite match what the software wants with what the hardware is providing. So today, by and large, systems, hardware create these strict hardware-software interfaces where we try to create a world where the software is running on the ideal, highly reliable system. So one example would be a piece of hardware that provides the abstraction of reliable storage and flash memory, where the software doesn't have to worry about any errors that might crop up. All the wear leveling is done in the hardware or in the firmware of the flash translation layer. So, we can try to make hardware perfect. We can minimize the consumption of the energy, consumption of the power with, say, subthreshold circuits. But if you work with, say, beginning undergraduates, you'll learn that it's very easy to find someone who can create software that will make your hardware perform terribly, right? I'll give you the example of the Prius, right? You can have the hybrid car that has the very good energy consumption profiles, and yet if you use software like a GPS that sends you through these clover loops endlessly, you're just wasting energy because the software is not being intelligent about how to use the actual hardware. So I think it's really a problem of the software and hardware mismatch. And so the question I'd like to pose today is, well, what if we just have the software demand less reliability from the hardware, because maybe that'll allow us to save energy. To tolerate less reliability, sure. And so that's the question we'll explore today. It's of course a very undesirable thing to make a system more unreliable, but we'll see what kinds of energy we can save by doing so. So the approach I'm going to take here is let the unreliability shine through the hardware-software interface. It's okay to have errors pop up. So these errors are going to permeate from the hardware up into the software stack. This is, in a sense, going to create an incentive system where the software is going to be more aware of its energy consumption, or perhaps the libraries implementing routines in the software. So it ought to be less wasteful with that energy. It can make choices between trade-offs of energy and reliability. But of course, this could be a complete nightmare. If you're programming and your hardware is unreliable, that's just going to be a complete nightmare. So the tension is how to create these hardware-software interfaces where we can reduce energy consumption by more intelligently using the hardware, but still not making the programming more difficult. We'd like the programmer not to have to worry about all the nitty-gritty details that the hardware traditionally has supported. So I'll talk about a few different areas of getting computation to work well on unreliable power. I'm just going to focus on the first two, how to get storage to work well. In particular, how to use NOR flash memory on embedded microcontrollers at sub-specification voltages. And then the second part, I'll talk about how to compute when your system reboots about every 100 milliseconds. It's extremely difficult to get things done on a device that loses power so often. And I'll have to save the secure communication part for another day. All right, and feel free to interrupt with questions. Sometimes the hardware-software interface between the presenter and the audience isn't quite matched up correctly. So if I'm glossing over a fact that isn't obvious, just raise your hand. So the first part I'd like to talk about is how to use flash memory at extremely low voltages, what I would consider illegal voltages by manufacturer specifications, the goal being to reduce the energy consumption of an embedded system. So this is a data center, not exactly the most cleanly data center. Well, I guess they have cable ties. And many people think of this as, well, the storage is going on in all these servers here. But when I look at this picture, I think, well, the really interesting storage is going on in the ceiling. So if you take a look in the ceiling, there's a smoke detector. And this device has some really interesting storage going on. It has embedded flash memory in that guy. Right? That's really interesting. And how often do you change your, I think everyone's going to change your batteries this weekend, right? With a time change, right? No?
Every 10 years.
Every 10 years?
Well, apparently the lithium 9-volt cells last that long in theory.
Ah, okay. Interesting. Well, I've got a video on Dropbox from a smoke detector company if you'd like to know about how they choose their batteries. But anyhow, let's take a look at inside these kinds of embedded devices to understand what's going on with storage and its relationship with energy. So again, we're talking about extremely embedded devices. I would consider these sort of these boring but high volume but important devices, things from thermostats to utility meters to implantable medical devices. But what I'd like to focus on at the moment is a smoke detector to understand where the joules are going as dictated by the flash memory. So I asked my students to have this 100 microcontroller party in 100 days where they would collect 100 products over 100 days and then take a look at where all the energy is going and analyze all the part numbers to figure out how the designer chose certain parameters of their system. And for this particular device, I thought it was interesting. It contains this microcontroller. It happens to be from Microchip, and it's got 8 kilobytes of embedded flash memory. It happens to be NOR flash memory. It's very rare to find NAND flash on these kinds of devices. And if you take a look at the spec of this particular microcontroller, it tells you, well, there are two basic voltages you can use as the supply voltage to your chip. If you just want the CPU to operate, you could run it at 2.2 volts. But if you'd ever like to write to flash memory, you must run it at 4.5 volts. So this creates a hard choice for the person who designs the board, because now they have to decide which voltage do they run it at. So in the ideal world, you'd buy a microcontroller and you'd have, say, 2 power rails or 2 pins on your chip, one for the low voltage and one for the high voltage. You can imagine many subcomponents of your microcontroller, but 2 interesting ones are the CPU and the flash. Now, the CPU typically can run on a relatively low voltage, but flash memory has a rather high minimum voltage requirement. It has a rather fancy charge pump just to get the voltage up high enough to write. So typically, you have this high voltage. Now, in the ideal world, you'd have the 2 pins such that if you don't write to flash memory, you would just not even bother turning on the high voltage line. Just don't draw any current there. And in that case, you'd have energy proportionality. Just like in the data center case, you'd be scaling with your utilization. In practice, it's not quite so good. In practice, due to cost constraints, the chip manufacturer only gives you 1 pin for your voltage source. And that 1 pin sort of has to rule all the different components on there and feed them the same voltage. So what happens with the system integrator? They look at all their components and they say, well, which one has the highest minimum voltage? That's the one we're going to run our system at 100% of the time. And so typically you'll find them running at this high voltage, whether or not they're writing to flash memory, but just in case they might write to flash memory at some point in the future. And there your energy consumption is going to be proportional to the worst case workload. And worse, don't forget that power consumption is proportional to voltage squared. So there's a squaring effect going on when you run on at a higher voltage. Our CPU is basically burning up energy unnecessarily, running at a high voltage that it doesn't need to get its job done. So we'll be looking at just how do we relax these constraints to run at a lower voltage and yet not have to worry about errors. And so today we have these sort of strict storage interfaces where an application developer expects highly reliable storage. So if you were to write a 0 into your flash memory, you would expect that it would actually be stored as a 0, and then later when you read it back, you would expect that 0 to come out. And this is done because we're running our flash memory at a relatively high voltage, and we have a reliability mechanism built into the hardware to do so. And it does a correct job. So what we're going to explore now, however, is, well, what if we move that reliability mechanism from the hardware layer and put it into the software stack instead? Instead of having this hard interface between the hardware and software, we're going to let errors propagate up. This is sort of like UDP for storage in a way. We're going to have sort of best effort storage in the hardware. It's going to try, but it doesn't guarantee, doesn't have strong guarantees, and the software is going to have to cope with that. But as a little bonus, we're going to be able to run the hardware at lower voltage and therefore save on energy consumption. This is not a particularly new idea. Actually, von Neumann, who I guess invented pretty much everything in computing and game theory, he had this fantastic paper in the 1950s on how to build reliable organisms out of unreliable organisms. And it was sort of the birth of stochastic computing, which last held its conference in 1978. But stochastic computing is coming back in vogue because of a lot of these energy constraints. So we're going to try to do the following, where we create this interface where if we write a 0, for instance, the hardware might actually screw up and write it as a 1 instead. And then later when it's read back, the software is going to have some kind of coping mechanism to handle those errors and to at least mask those errors or correct them. All right, so I'm kind of a history buff, and I see you have things in your lobby as well that are interesting pieces of computing history. Has anyone used a punch card? Awesome, okay. I loved playing, so this is going to date me, but I used to love playing with my father's punch cards. There's some interesting things you can do with needle and thread and punch cards for parallelism. But anyhow, this is your typical punch card system, and it's a write-once storage medium, which is sort of like flash memory if you don't think of the erase operation. And it turns out, I started looking through the literature, and it brought me all the way back to my thesis advisor. It turns out he wrote a paper in 1982, Revest and Shamir wrote a paper on how to use write-once memory and turn it into rewritable memory, even if you can only write once. They called these write-once bits, or WITs. And the basic idea was that they would use coding theory. So you can imagine if you punch something into a punch card and you want to reuse that previously punched punch card, it's okay as long as the next value you write is sort of a superset of what you previously wrote. So just reuse those bit patterns. So we're going to do something very similar. We're going to treat flash memory as WITs, these write-once bits, but slightly different. We're going to be running it at a low voltage, an illegal voltage, which is logically going to produce sort of hanging chads. We may not properly punch our flash memory, and we'll get these errors. We're halfway writing, so we call these half-wits. We're going to have these half-written write-once bits, and we're going to use our flash memory in a manner inconsistent with what the manufacturer dictates. In case you haven't guessed yet, I don't like authority. So we're going to use their system illegally. But the good news is we're going to be able to run it at a lower voltage. And that translates into lower power consumption. And that typically translates into lower energy consumption as well. The bad news is our storage system becomes probabilistic. So the big problem is, how do we reliably store data on this unreliable mechanism? So there are a bunch of ways you could do this, depending upon what's your cost factor. So the typical way, the typical approach is you just pick the highest voltage, and so that you can run your flash memory reliably. But this leads to this excessive power consumption. You could also choose to implement what I would call sort of the poor man's discrete voltage scaling. You can add some discrete components to the outside of your microcontroller to dynamically adjust your voltage. In practice, manufacturers don't like this because they don't like to buy 2 voltage regulators or an adjustable voltage regulator. It's just cost prohibitive, adding just a couple discrete components or even a couple transistors. The manufacturers will just kick you out of the building if you ask to spend one more penny on adding a piece of hardware to these high volume devices. The other approach, and we found this is sort of what motivated our research, was just don't use flash memory. So when we got our hands on one of the early Intel WISPs, we were really excited. They told us it had this embedded flash memory. We were doing our crypto. We were going to checkpoint some state. We wrote all the code. We did the checkpoint, and it didn't store. So we asked the designers, well, why isn't it storing? And they said, oh, you're going to use the flash memory? Well, we run it at a low voltage so that it lasts longer, but unfortunately that means you can't use the flash. So the flash was just sitting there teasing us, but we weren't able to write to it. So we're going to write at a low voltage. We're going to get errors, and we're going to have to correct these errors. And so it's the typical game of, well, are we going to be able to actually ultimately save energy in the long run, even if we have to pay for that overhead of having to correct any potential errors? And I'll just give away the end of the story. Yes, for many workloads, we're able to actually have a net decrease in energy consumption for the same workload by running at a low voltage, despite the error correction cost. And we'll get right into some of our methods and methodologies for measuring this. So we attempted a whole bunch of different ways to add reliability at the software stack. You can think of it as sort of a software driver. I'm mainly going to focus on one technique that we found overwhelmingly better than all the others. It's called in-place writes, as opposed to more traditional error correction codes, which we found surprisingly worked terribly. But the in-place writes algorithm, I think, is a very simple one that's very easy to understand. It's a very simple feedback loop. The hard part is understanding why it works so well. So traditionally, you just do a write in your software, but we're going to replace every single write with the following feedback loop. We do the write, and then we read it back at this low voltage, and we see if what we read back matches with what we were trying to get stick into the flash memory.
So reading is always reliable, even on a low voltage?
Reading is always reliable. CPU and reading is always reliable. And we've done testing to make sure that the reads, it doesn't change its value over time. It could, but we haven't found any cases. So we do this read, we check if there's an error, and if it didn't work, we just try again. We keep writing in place to that same location again and again and again, and when the error goes away, we're done. So all NOR flash memory is born as ones. I don't know why they chose one, but that's what it is. And so when you attempt to do a write, let's say you like to write this value where the two least significant bits are 0, you're basically trying to flip those two LSBs. And if you're running at a low voltage, you might get an error. So for instance, in this case, we had a bit flip error where we were not able to accumulate enough charge on the floating gate to have it represent itself as a logical 0. So there's an error that we're going to have to correct using our feedback loop. But what's interesting, because these are born as ones, this is what's known in coding theory or information theory as a Z channel. If we'd like to do the operation where we write the bit value 1, there's a 0 probability of failure. It will always work. But if we wish to write a 0, it might fail with some probability p. And so you can begin to explore different kinds of coding to exploit this asymmetry that doesn't usually turn up in most computing systems. So we'll get into this in a little bit. So there's a whole bunch of factors that will influence the energy performance of this rather simple feedback loop. Here are a few of the different properties we took a look at. And today we're just going to cover this first element, which is the most important one, and that is how does your choice of the voltage supply impact your error rate and your overall energy consumption using this particular algorithm. So from this is our one eye candy picture. And you can learn a couple things from this picture. Number one, we're using a programmable power supply so we can get fairly precise. We can fairly precisely set our voltage supply. And second, you can tell that we're software developers from our wiring. But we're running our algorithms on this first device, and because the actual monitoring of the system cannot be run on the same system under test because it would consume energy, we have a separate system to actually measure what's going on in the storage system. Okay, so let's take a look at what happens when we run our system at a illegally low voltage and we get errors in flash memory. We're using the Texas Instruments MSP430 microcontroller, which is a fairly popular ultra-low power microcontroller. And it's designed, the spec says we need to run it at 2.2 volts to get a correct write. So we're running it as low as 1.86 volts, at which point we're getting no errors at all. This, for each one of these dots, represents the average of 50 trials. I call this the slide of 1,000 missed lunches of my poor graduate student. And we don't have error bars because it's basically 1%. So there's very little error in this case. But as you can see, as we approach 1.84 volts, we suddenly hit this wall where we get a terrible error rate, and we very quickly shoot up to 100% error. So that was one microcontroller. We didn't stop there, right? So we tried a different microcontroller from the same model, and we got the same shape of error, but at a very different voltage. And this is due largely to process variation. You can expect this. This is why a manufacturer sets a relatively high safety margin, so they don't have to worry about the process variation. Yes?
Were you just writing or also erasing?
This is just writing it. Erasing, there's some interesting complexities to erasing because of the segmentation, but this is just writing. But we can talk about erasing at the end if you'd like to know more about the complexities. So we took a different microcontroller, a different model, and you'll again see different places where you start to see errors. There's actually one microcontroller where we got all the way down to 1.8 volts and we couldn't get it to produce any errors. We had to make sure that we only used each microcontroller once because of wear leveling. Every time we used it, we had to basically throw it away. So we had to eat up a lot of microcontrollers for these experiments. But what you can learn is that statically, the static approach of just picking a voltage at which you think you won't get errors is not going to work because it's likely going to change over time. It's going to vary by temperature, and it's going to vary by device. So what we're going to want is a software system that can adapt to systems that had different kinds of failure properties. The other interesting thing we're going to exploit to make our system work well is what's known as the accumulative property of floating gate transistors. So this was a weird journey for me because I'm a software guy, but we found that our software was tickling an interesting property of some of the hardware. So to explain why our system is going to actually perform so well, pardon me if you're a hardware designer or a circuit designer, this is going to be my interpretation of how floating gates work. And I always mix up electrons and holes. But imagine you have a single floating gate transistor that's representing a single bit. This is currently the bit with a logical 1. But if you apply enough charge, if you put charge into the floating gate there, then it begins to change its value into a 0 once you accumulate enough charge. That's how flash memory, NOR flash memory works, by storing this charge in here. Now, what's interesting is that because of that accumulative property, a failed write is actually a partial success. So what our feedback loop exploits is the following. When we do, say we want to flip this 1 to a 0, we do it at low voltage, and the first attempt didn't work out. We got an error because we didn't accumulate enough charge, but it accumulated some charge. So the second time we attempt to do a write, we get over that threshold, at which point it's interpreted as a logical 0. Question?
So you said before that you have this Z model where you go 1 to 1 to 0 and you never go back to 1 again.
Correct.
But if you're with this accumulative model, if you accumulate up to the point where you're right on the threshold, and then maybe the temperature of the chip changes, or the supply voltage wobbles a little bit, could you not go backwards?
It is theoretically possible, and we explored the question of can we get this sort of instability where at different times or temperatures would things differ. All I can say is it is possible, but in all of our testing, we have yet to see any bit flip that goes backwards or changes its direction. So one of our experiments involved writing to flash memory in this manner, and then we stuck it in a quiet location for 3 months and then read it back again, and we could find no bit errors. It is theoretically possible, but we haven't found it. All right. So the name of the game is, again, the balance. It's a trade-off. So we're going to run our system at low voltage, and because of that magic v-squared property, it's going to have significantly less energy consumption. But we're going to have an extra cost of this penalty for adding back reliability in the software stack. And the big question is, when is it going to be less than the energy of the overall workload? How do we run it at a high voltage the whole time? So to measure that, what we did was, this is a very standard technique in measuring energy consumption. We're using what's known as a sense resistor, a very small resistor, to measure the current consumption of our microcontroller. So we're able to compute the current consumption by the voltage drop across this sense resistor. And then on our oscilloscope, we take a trace, and we send a GPIO high to denote when the workload is starting and stopping so we can get exact measurements of time. And then you throw it through a very simple MATLAB integration to compute how much energy has been consumed by a particular workload. So that's how we're going to be measuring the energy consumption of our different approaches. All right, so with that set up in mind, the first thing we did before actually computing how much energy was consumed was just how often do we need to go through this feedback loop to get a reliable write. And so we ran our system at various voltages. You can see if you run your system at 1.9 volts, we never got any errors, and so we never had to execute that feedback loop. But if you're a little bit more on the risky type, if you're a risky kind of person and you run it at 1.86 volts, you can see that we started off with 100% errors on our first attempt to write, and it may take you up to 6 rewrites to get a nice write there. That's how many attempts it took to accumulate enough charge. So this gives you a hint that, as you can see, if you were to choose 1.9 or 1.89 volts for that particular chip, you would very rarely need to execute your recovery mechanism, but you're still able to shave off quite a bit of your safety margin. Okay, so let's go right into some micro benchmarks. It's hard to find workloads for these systems, so we're going to have to rely on some, mostly on micro benchmarks and sensor networking benchmarks. So this benchmark is comparing this first benchmark is comparing how well the RC5 symmetric cipher runs on our system versus a high voltage system. It's a very CPU intense operation. Where we happen to be reporting the average of 5 trials. So when we ran this RC5 encryption, it consumed 43 microjoules, which was about 26% less than if we had run it at a high voltage. Now, the reason why we're able to get this reduction in energy is not because we're making the flash memory any better. It's actually because we're making the CPU run better. It turns out every time you run the CPU at a high voltage, it's consuming unnecessary power. So all of our gains come from running the CPU lower, even though we're paying a little higher price when we do a write to flash memory. So I also have to show you the worst case scenario for the system, and that is paradoxically writing to flash memory. So if you do a write to flash memory, because of that feedback loop, in one case, for some very strange reasons actually, one would expect it to run about the same, but it actually is about 300% worse if you try to do a write. So if you have a write-heavy workload, you wouldn't want to do this, right? Now, the good news is in practice, most embedded workloads are not strictly write. In fact, most of the workloads we've seen in practice and from industry are more of the flavor one write for every, say, 1 million CPU cycles, typically accumulation. Question?
So it seems like what this is saying to me is that flash controller should be doing the read after write, and my impression is, at least for multi-level NAND, it already does a sense. It's already a trigger, right?
You're getting somewhere. So that's exactly correct. So I went to Rambus. The Rambus is that lovely company that owns all the patents so they can sue you about memory. And I asked them, why the heck is my system performing so well, especially on these CPU-heavy workloads? And I said, why doesn't your hardware do this? And they said, well, you know what? The hardware does have a feedback loop very similar to the one you're implementing. But the problem is, it's the classic end-to-end argument for system design. Because the hardware has to work for all software, it chooses a very conservative approach, and that is it minimizes delay. It says, our spec says our write needs to finish after a very particular delay, because some application might want it to finish in that amount of time. So it terminates its loop early. It's not able to just have a sort of a while loop until the write sticks.
And this is observable? You observe this? Or somehow can you observe this?
I'd like to observe that, but this is what I'm hearing from the circuit designers, that it's very typical to have a feedback loop, but because they're required by the spec to finish within a minimum certain delay, they're not able to have a loop that keeps going as long as ours.
So in these experiments, the controller is already doing this, but because it aborted the loop, it's reporting an error. And
Correct.
those are the errors you're seeing.
Yeah.
Correct.
And then you're running it again.
Correct.
Okay.
I should note that there is no flash translation layer. This is a very bare bones microcontroller. They do have the circuits to apply to the floating gates, but there's no wear leveling or anything of that nature. That's all manual. All right. So anyhow, that's basically the same slide. If you're willing to play even a little bit more fast and loose and run your system at 1.8 volts, you may more often have to use your recovery mechanism, but we're still able to reduce the overall energy consumption by 35%. And what's interesting to me is that the workload at 1.8 volts actually runs more slowly. It takes significantly more time than running it at 2.2 volts because it's the good old combinational logic takes longer to finish at a lower voltage. So we're taking longer, but even though we're running the system longer, because we're running at a lower voltage, if you integrate over time, we've used less overall energy. So the other benchmark is the closest thing we can get to an application level benchmark. So we took a look at a typical sensor networking application, is monitoring the environment, for instance. So we're reading 256 bytes from our onboard accelerometer, and we're computing some very simple statistics, and then we're writing those aggregated statistics to the NOR flash memory. It happens to be 256 bytes. And then we report the average of the 5 trials. And so we get very close to that ideal workload of a very CPU-oriented workload, reducing the energy consumption by about 27% by running it at 1.9 volts rather than 2.2 volts. And just to give you a feeling of the power consumption difference between these two voltages, running our CPU at 2.2 volts is about double the power consumption because of that V-squared operation. And again, if you're willing to run your system at 1.8 volts, you can get down to about 34% less, which is getting pretty close to the best you could do. All right. Oh, question?
So on that curve you showed, there was with how Rice performed, you had errors of 100%, and the curves moved, right? For you had errors of 100% at 1.86 volts. So you'd have to write many times then, or exactly, or maybe that would never. So this is for one of your MCUs. I'm
correct.
Referring to the
this is for one MCU.
Where,
in this particular graph, we're using one MCU. That's
but
right. And you're going to.
It's possible that you might find yourself going, okay, I can use 1.6 volts, and then it's particularly warm or cold, or it's a Tuesday or whatever, and actually this loop runs forever and never actually manages to write the bit out.
So if it were cold outdoors, you'd be correct. But actually the interest, let me see if I can find our thermal check here. What's interesting is at higher temperatures we perform better. So we get about a 63% error rate when we're working in our laboratory, but nearly zero errors if you get up to about 39 degrees. But if it is correct, temperature will influence the performance of those floating gates. So what we typically recommend is know your workload and know your intended environment. If you're expecting to be in an environment that's going to have huge fluctuations in temperature, then you're going to need to be more conservative. But if you have information, then you have conditional probabilities, and you can choose a system that's more appropriate.
Just one very concrete question. How many instances of the MCU are these results based on averaging across?
Well, each of those points, well, for the very first one, it was 50, but for all the others, it was 5. And I've forgotten how many 100 microcontrollers we burned through, but I'll have to get you that number later. It was a lot of government money put to good use.
And you said the MSP430, you were saying that the spec says you can drive it, you can run the flash memory at 2.2 volts, whereas with your PIC it was 4.5 volts for writing to flash, but for an MSP430 you can run.
For an MSP you can run relatively low. The MSPs used to require that you run your system at 3 volts, and then I think a year or two ago they were able to get down to 2.2 volts. What's interesting is from a circuit perspective, one of the reasons why you can run it at lower and lower voltages is because they put special circuitry called charge pumps into the flash memory. And the interesting thing about a charge pump is it has an efficiency, which is usually quite poor. So there's an argument that maybe you should be removing some of the hardware that does this charge pump that boosts the voltage up to a higher voltage in order to make it more efficient. But the MSP does run as low as 2.2 with correct behavior.
But it has got a charge pump in it, right?
It does.
And the PIC does not have a charge pump, or is that also?
I don't know. These are very proprietary designs, and so I often rely on friends who there happens to be one guy in Pennsylvania who likes to decapsulate chips, and the companies refuse to tell us what their circuit designs are. It was hard enough just to learn that it had 3,000 logic gate equivalents.
But I'm kind of guessing that the manufacturers would try and spec their systems so that the flash memory fails at the same point as the CPU would fail, right? They're going to choose the step up of the charge pump such that you can run the whole system at the very lowest voltage. And sure, the charge pump isn't that efficient, but like you said, you're not using it that often. You're not doing those writes that often.
That would be nice, but I'm not seeing that in microcontrollers such as the MSP430. There may be some systems in the future that can, but I suspect it's going to be because of these charge pumps, which doesn't mean necessarily that it's more efficient.
So I'm guessing that you've basically proven that you can run this thing at 1.96 volts instead of 2.2 volts. And
well, no, I don't think you can really. Well, that's also conditional on temperature. Basically,
exactly. So
I think all we can.
The manufacturer's going to have this range of temperatures, operating temperatures, right? That they're trying to do is run it as close to the wire as they can, but they want to obviously maintain their specs, not.
But that's because their spec follows the notion of sort of very strong guarantees of reliability.
Yes.
And we're saying let's explore a different direction. Let's just explore how good we can get the system if we don't have such constraining requirements on the hardware. In other words, we're going to feed the hardware a better workload to make the hardware perform better. It's the good old argument of like microkernels and simplicity as the closer you get to the hardware. We're going to keep it as simple as possible and put more of the context-sensitive logic up in the software stack.
I think your work would be much easier if you would have collaboration from the hardware manufacturers. For instance, if they would return you whether the write was successful, then you could decide by yourself whether to continue. And so
that's actually a good point. What we'd really like to see is some architectural support to give away certain hints. Right now, most of this energy, all these issues are just hidden. Even if the software wants access to it, they don't get access because the ISA doesn't expose that. There's some really interesting things you can do by opening up the ISAs to make this hints more available. So I should probably move on to the computation story. Looks like I got about 20 minutes remaining or so. I think I can get through it. So the next thing I'd like to talk about is just how to get computation to work well on intermittent power when you're rebooting about every 100 milliseconds or so because of energy shortfalls. And we're basically going to be doing checkpointing. And I'm sure most of you are familiar with checkpointing. It's very popular in distributed systems and the dependability community. And the name of the game is we're going to try to avoid what we call Sisyphean tasks. So imagine you've got this computation, you're rolling your rock up the hill, and every time you get near completion of your computation, you run out of power and you drop it, and you got to start over again. So we're going to try to get long-running computations done despite these very continuous interruptions to our power. We took the Intel WISP and we modified it a bit, so we started manufacturing our own device. It happens to be called the UMass Mu. Actually, here's our handy-dandy pamphlet. There's some flyers outside if you'd like to know more about it. But what's interesting is it's running off a 10 microfarad capacitor. It has no battery, and it's doing all of its energy harvesting from this 915 megahertz tuned antenna, getting the energy from an RFID reader. And because of that, we get very fickle energy. It's really hard to predict what kind of voltage our processor is going to see. So the capacitor helps us buffer, helps us smooth out that voltage. But even so, it fills quickly and it gets used up quickly. And this leads to frequent reboots. So in the supercomputing world, such as mobile phones, now I think of mobile phones as supercomputers because they have, I think, 8 to 10 orders of magnitude more energy than this device. But on a typical device where you have a long period of time, you can effectively think of it as having infinite energy. Maybe not George's phone, but infinite energy. But in our case, we're living in this horrible world. So these are 3 traces of the same human activity. What we did was we chopped off the front end of our energy harvester and put it through our oscilloscope. The units aren't particularly important, but it's just the student holding this device in front of the RFID reader and then measuring the voltage. And you can see you get radically different traces for each one. It's very difficult to predict what kind of voltage you're going to see from the processor perspective on these kind of fickle energy harvesting devices. Just to give you an idea of just how painful it is for programmers to use this without architectural or without OS support, this is a real plot of every time our system rebooted. So my student created this lovely guy. Every time it says reboot, his system was actually rebooting, and he lost all state, all RAM, all registers, all went away, and he had to restart his computation. And again, that's what we call the Sisyphean task when we drop our computation and have to recompute it from scratch. So intermittent power makes programming a real pain in the neck. The constant power loss, and this is not just the typical computer system thinks of power loss as a rare event where you need a coping mechanism, FSIC on your file systems every now and then. In this case, we're actually going to be rebooting more often than we're computing, most of the time. So the goal here is to find simple abstractions to help programs and to help programmers tolerate these highly unreliable energy sources such that you don't have to think about it when you're programming your system. So these are energy-aware checkpoints, and I found out you already know about reality checkpoints. I found that lovely guy in the green over there. But we're going to checkpoint. And the hard part here is going to be doing energy-aware checkpoints at such an extremely small scale. But it's instructive to look at just how this problem is solved today. Oh yeah, actually we got the London Oyster card. Who uses Oyster around here? Okay. So the London Oyster system was extremely innovative, and they made a fundamental contribution to contactless payment systems. The way they solve this reboot problem is they constrain the problem. They say if your computation takes longer than 300 milliseconds, you're not allowed to do it. And this way they're able to have guarantees at the hardware level that if the computation starts, they know they're going to complete it. But if you want to write something that takes 301 milliseconds, you go away. You're not allowed to do that. This is not a Turing machine. So we'd like to relax these constraints to make general purpose computation more feasible. Now that doesn't mean we're going to be fast, but what it means is if we can find a way to get done with the energy we're provided, we're going to have a pretty good chance of completing it eventually. The interesting thing about 300 milliseconds is how they actually chose this number. They created artificial latencies on the bus system in London, and they found out that after about 300 milliseconds there's extreme frustration by passengers. So that's why the 300 milliseconds exists globally now as the standard for contactless smart cards. So our approach is relatively straightforward. We do these checkpoints, and we try to do the checkpoint before we reboot, because we're going to try to insulate the programmer from all this unreliability. So just to give you an idea of how this works, checkpointing before failure is the following. So this is our voltage supply. Again, we're not your typical computer. We're not running on a constant voltage. Every time we run our computer, we've spent a few joules, and that means our capacitor loses voltage. So we're literally computing as we're losing voltage and losing energy. So as we get closer and closer to 1.8 volts, which is where our CPU may begin to fail, we need to checkpoint. So you can imagine you have your computation coming down, and you do your checkpoint right before you die. And then when you have enough time to recharge your capacitor, you can then resume, do a restoration, and continue on with your computation. And so the name of the game is splitting up the computation into these smaller pieces, spreading the computation across reboots. And what we checkpoint are the registers, the stack, and the globals. So it's a variable amount of data that we're going to checkpoint at these critical times. So I thought this would take just a few weeks, and it ended up taking a couple years. For instance, there were all sorts of development problems like LLVM not having a back-end support for the MSP430 machines. We had to create that. But there are other hard parts too. When checkpointing, we're checkpointing when we have sort of dangerously low amounts of energy. And you might recall from the previous talk, it's also when we have the flash write is sort of the worst thing you can do when you have very small amounts of energy. So you're really on thin ice. To give you an idea of just how much energy gets consumed, if you want to just ask your system, am I getting close to death? That has a penalty of 100x compared to a CPU op. So just asking if you're about to die makes you die more quickly. And then if you know you're going to die, there's also a 100x penalty to do the actual checkpoint itself. So we want to avoid these checkpoints if possible. And then the variability of the actual data also adds some uncertainty to the whole picture because we don't know exactly how much energy we're going to need to reserve sort of headroom on our capacitor to get that checkpoint to stick. So I'm going to use one running example. It's a toy example, good old CRC, but it exercises many of the interesting things to understand about checkpointing. Running it on our processor takes about a little more than half a second when we don't have any reboots. So since our system does reboot about every 100 milliseconds, we are going to see these problems where we have to do checkpoints. So let me explain how our system works from the programmer's perspective. We'd like to make sure the programmer just has to think about writing their code, not having to worry about energy. So we're going to try to help the programmer choose certain energy-centric parameters in how the checkpoints are done. So Mementos is effectively a library that you link against. It happens to be implemented in LLVM because we were extremely frustrated with the modularity of GCC. But LLVM is wonderful because you can add all these nice optimizations in their intermediate representation. After we throw our system through LLVM to make it energy aware and add the checkpointing routines, we simulate the program in something called MSPSim. We augmented that with the notion of energy awareness. And this helps us choose certain parameters for our checkpointing strategy, at which point we can dump it to hardware. So we've divided up the checkpointing into sort of two major pieces, the compile time, the static decisions, and then at runtime. So at compile time, what our job, the name of the game, is to remove checkpoints. We're going to try to just mark places in the code where we might want to do a checkpoint in the future. So, for instance, the end of a loop latch, you might expect some state change. That might be a good place to do a checkpoint. Or a function call return where you're popping the stack. You know, you're going to have large fluctuations of your memory. Maybe that's a good place to do a checkpoint. So statically, it's not that we're adding checkpoints, we're actually removing checkpoints. We're saying there are certain places in the code where we never want to checkpoint, and this helps us avoid checking our energy unnecessarily at runtime. But there are a few other instrumentation strategies to choose where you might do a checkpoint. Now, at runtime, we need to make decisions based upon how much energy we have left in our 10 microfarad capacitor of whether we actually need to do a checkpoint. If it turns out we have a surplus of energy, we might be able to avoid the checkpoint entirely. So we're going to try to do that. Now, unfortunately, we have at our disposal very few things, very little architectural support for checkpoints. So what we use is a proxy for death. Our proxy for death is a threshold voltage, not a circuit threshold, but a voltage at which we believe we're likely to die. So if our death period is around 1.8 volts, and we're doing our checkpoint, and it's going to have some amount of time it takes to finish, you could checkpoint conservatively, well before you get to this point of death. But if you do that, you've actually wasted quite a bit of time. The problem is this energy basically just drains away. But worse than that, you've shortened every single life cycle such that you've chopped off a little bit. So you're going to increase the number of overall reboots to finish your computation. So what we really want to do is checkpoint as close to death. Now, if you checkpoint too late, obviously you're dead and you have to start over from scratch. So we also want to avoid that case. What we really want is that Goldilocks checkpoint right before death. Get as close as we can to that flat line. And to do that, we have the abstraction of this threshold. We choose statically 1 voltage. It's a proxy for death. It's not the best one, but it's the proxy we use to choose when to checkpoint.
You shouldn't need to start over, right? You can afford to miss a few checkpoints. You'll just start from the last checkpoint.
That's correct. So there are some cases where we are willing to actually be a little more risk-taking and get close to death. It doesn't work so well for non-idempotent operations like launch missile, but for most of our applications, we're fine with restarting our computation. But still, we'd like to avoid it if possible. All right, so there are plenty of other ways you could do the adaptivity, but we're using this voltage threshold. Let's move on. So one of the hard parts, though, is making this reproducible. If you've ever worked with energy harvesting, every time you do an energy harvesting trace, it's different. So the first thing we did was we tried to make this reproducible. And the way we did that was we took our device and we literally sliced off the front end. And we would take our energy measurements through our oscilloscope, and then we would simulate the behavior of our capacitor, sort of physics 101. And then we'd throw this into our specially instrumented MSP simulator that's now energy aware. It has the notion of that certain operations consume different amounts of energy depending upon the voltage. And it helps us understand when our system reboots. So to give you an idea of how the simulator works, after you run it through LLVM, if you give our simulator both the binary and the voltage trace, it'll tell you how your system's going to behave. So in this case, we fed in the following trace. This blue line is what the harvester is effectively seeing from our 10 microfarad simulated capacitor. And the green line is what happens after our five-stage charge pump. So it boosts up that voltage. After we get up to about 3.2 volts is where we decide, our voltage supervisor decides that we have enough headroom to start the computation, and we turn on our processor, and very quickly we shoot down to death. We're just riding the roller coaster of death. And then this red dot is where we do a checkpoint, right before we die. As you can see, it takes about the same amount of time to recharge back up until we can do a restoration on the green dot and continue on. And we continue doing these reboot restoration cycles. So what's interesting is if you start to think about, so this is all heuristics, right? And there's no relative, there's no way to compare it really with what's the ideal. So what we decided to do was to create an oracle that could, for reasonable workloads, we created a greedy algorithm that can tell us what's the best case scenario. It's going to try every conceivable checkpoint strategy, sort of, using a binary search. And it's going to try to find even ones that we could not possibly create on our own. It'll tell us what's the best case scenario. So the way we do this is we re-execute code. This is the beauty about MSP 430 simulators and LLVM. So we run our system and we do a checkpoint. And if we find that we checkpoint just fine, then we say, well, let's be a little more risk-taking and checkpoint at a lower voltage. And then if we die, we say, oh, we got that wrong, so we're going to backtrack, and we're going to do this binary search until we can find sort of the perfect voltage threshold at which we get pretty close to death, but we don't actually go past it. Yes?
But surely it's not monotonic. Not seeing how binary search.
Right. Well, so it is. So it's not exhaustive. That is correct. It's only going to work on smooth cases. That's right. But the oracle basically tells us for these smooth cases what's the best case you could ever hope for in terms of how many reboots it would take as well. So to give you an idea of what happens when you compare it against the oracle, again, here we have our lovely CRC, and it's running a little more than half a second. When we run it through our oracle, it tells us, well, on this particular energy trace, here's how the behavior of your program is going to perform. If you're running the oracle, if you choose what it thinks is the best case checkpointing strategy, it's going to take you 14 reboots, and it's going to take you about 685,000 CPU cycles running around 4 seconds. Now in practice, when we run it without an oracle, with an actual checkpointing strategy that's programmable, we're not quite so good, and we actually run it at a slightly higher voltage just because voltage regulators typically come in discrete sizes. But what might surprise you here is just certain incongruencies. So this is your typical system where it's not going to perform as well, but we are at least going to be able to perform. The previous system wouldn't work at all, but we get a 30% blow up in the number of CPU cycles. That's as a result of all the instrumentation. But the weird thing is, for some reason, we take 10 times longer wall clock time. And so there's this weird discrepancy between the 1.3 and the 10.7. You would think that they'd be about the same. And so this puzzled us for a minute, but then when we looked at the graph, it became obvious. Oh.
That number isn't 10 times bigger than the other one. Is it something else?
This is compared against the uninstrumented. I'm sorry. So, yeah. So the uninstrumented code versus our best case execution was 30% worse. But the wall clock time was actually 10 times worse. And the reason for this discrepancy, you can tell just by looking at the bottom graph. Half of the time was just spent warming up our capacitor to charge up. And you don't get that in a system that has infinite energy. And then if you look at all the reboots, you see that over half of your time is spent recharging after each reboot. So that's why we have this large wall clock blow up. We don't have such a bad blow up in terms of the active CPU, but on these systems, you generally want to sleep well and perform good enough. And that's what we're trying to do. So in this comparison, if you don't have checkpointing, your system never finishes. You'd have to manually instrument your code to work. But with the checkpointing system, we do at least finish eventually after 16 reboots. So the idea with Mementos is that we'd like to let programmers just write their code, not have to worry so much about this. Don't worry about energy. And at compile time, we instrument your programs, and then at runtime, we checkpoint when we think it's necessary. There's some really interesting future directions. We've been experimenting with other non-volatile memories like FRAM. And there's some interesting things you can do with smarter checkpointing, compression, incremental, that turns out to be really hard when you don't have registers. When you're checkpointing your registers, it limits some of the algorithms you can actually implement in practice. But that is Mementos. Hang on. So I'm running a little bit over time. Maybe I'll just get to right over here. I think what I hope you leave the talk remembering today is that you can reduce energy by demanding less reliability from your hardware, and that errors are okay, as long as you have a coping mechanism that doesn't cost a lot. So in this case, there were two different mechanisms we tried. One with embedded storage, where we're running our system at unreliable voltages, and then we restore the reliability in software at a very low cost. And then for embedded computation, we're able to create these energy-aware checkpoints, so we can at least get things done eventually if there is a pathway to getting things done. I think I will just end there. And I'd be happy to take any questions, but I think I'm a little over time, and George is running my schedule.